Hey everyone, and welcome. Today we're diving into something that's kind of like the hidden muscle of our modern world. It's a device that takes something as simple and invisible as air and turns it into the incredible force that helps build our cars, opens our doors, and powers the factories that shape our daily lives. I mean, it sounds kind of crazy, right? How can something as light and, as intangible as air be harnessed to push, pull, lift, and press with such amazing strength and precision? That is the core question we are tackling today. Well, the answer is this amazing device right here, the pneumatic cylinder. The best way to think of it is as the muscle in any system that runs on compressed air. It's the component that does the heavy lifting, taking all that potential energy stored in the air and converting it into actual, useful work. So here's how we're going to break it all down. First, we'll look at the basic anatomy. Then, we'll get to know the two main workhorses of the pneumatic world. After that, we'll explore some really specialized designs, touch on the simple math that makes them work, and finally, we'll uncover where these things are hiding all around you. Alright, so let's jump right in and take a look under the hood. You'll see that every pneumatic cylinder, no matter how complex it gets, is really built from just a few essential parts. At its core, the design is just brilliantly simple. You've got the piston, that's the disc that moves back and forth inside the barrel. It's attached to the piston rod, which is the shaft that actually sticks out to do the work. Everything is held together by the end caps, and you have these crucial piston rings and seals that stop air from leaking out. That's what ensures all that pressure gets turned into pure movement. Okay, so now that we know the basic parts, let's get into the two fundamental designs that you're going to see pretty much everywhere. They form the foundation of almost all pneumatic systems. First up, we have the single acting cylinder, or SAC for short, and this thing is the definition of simplicity. Compressed air gets pushed into one port, and that forces the piston out to do a job. But wait, how does it get back? Well, you can see it right there in the diagram, that big internal spring. Once you release the air pressure, the spring just shoves the piston right back to where it started. It's great for simple tasks, but that spring does limit how far it can travel, usually to around 80 millimeters or so. And this brings us to the next logical step, the double-acting cylinder, or deck. Right away, notice what's missing. Yep, the spring's gone. Instead, it's got a second port. So compressed air pushes the piston out, and compressed air is also used to pull it back in. This is a game changer because it means the cylinder can apply force in both directions, making it way more versatile. So really, it all boils down to a trade-off, doesn't it? The single-acting cylinder is simpler, sure, and it uses less air, but its power is strictly one way. The double-acting cylinder gives you powered, controlled motion in both directions, which opens up a whole new world of control and potential. But engineers, they never stop at the basics, right? A whole family of really cool specialized cylinders has been developed to solve all sorts of unique and complex problems. Let's check out a few. Okay, picture this. You've got a cylinder moving a really heavy object, and it's moving fast. If it just slams into the end cap, you're going to get a ton of damage, not to mention a lot of noise. So, how do you solve that? Well, you solve it with some seriously clever design. This is a cylinder with what's called end position cushioning, and its entire job is to gracefully slow that piston down just before it reaches the end of its travel, giving it a soft, impact-free stop. So here's the genius of how it works. For most of the trip, air escapes easily and the piston is flying along. But right at the very end, a little cushioning piston slides in and blocks the main exit for the air. This traps a small pocket of air, which can now only squeeze out through a tiny adjustable channel. This trapped pocket of air basically acts like a brake pad, creating back pressure that slows the piston down for a perfectly smooth landing. It is just pure mechanical elegance. But it's not just about stopping smoothly. Other designs have to tackle challenges like force and stability. On the left, you've got the tandem cylinder. This is basically two cylinders bolted together, end to end. An engineer would pick this when they need almost double the force, but they're stuck with a limited amount of space and can't just use a wider cylinder. And then on the right, we have the through rod cylinder. See how the rod pokes out both ends? This provides amazing guidance and stops the rod from wobbling under load, which is crucial for precision work. It also means the force is exactly the same in both directions, perfect for any job that needs a balanced push and pull. And the innovations don't stop there. The multi-position cylinder on the left is pretty clever. It basically links two cylinders with different stroke lengths. By controlling which cylinder gets air, you can get 3 or even 4 distinct stopping points. And then check this out. The rotary cylinder on the right uses this awesome rack and pinion gear system to convert that linear push into a twisting rotational force. Okay, so with all these different options, how in the world does an engineer pick the right one for the job? Well, like a lot of engineering, it all comes down to the numbers. Engineers really have to nail two critical numbers. First is piston force. Exactly how hard can this thing push or pull? That's all about the air pressure you're feeding it and the surface area of the piston. If you get that wrong, your machine just won't be strong enough. The second is air consumption. This tells you how much compressed air the whole system is going to need. If you underestimate this, your compressor will never keep up and you'll end up with an expensive, inefficient system that fails under pressure. Literally. Now, here's a really subtle but absolutely crucial detail that engineers always have to account for with double-acting cylinders. So look at the forward stroke, right? When the cylinder is extending. The compressed air is pushing against the entire face of the piston. You get maximum force. but on the return stroke, the piston rod itself is in the way. It physically takes up space, reducing the surface area that the air can push against. And what that means is the pulling force is always just a little bit weaker than the pushing force, a critical detail you have to plan for in any design. All right, we've gone through the mechanics, we've touched on the maths. Now let's bring it all home and see how these amazing devices are the quiet, powerful workhorses all around us. This quote right here, it's a perfect real-world example of the kind of problem statement an engineer gets. The goal isn't just to pick a cylinder, it's to design a whole system of valves and controls to get a specific result. In this case, making something move back and forth, over and over, but only when a button is being held down. This is the kind of logic puzzle that gets solved with these components every single day. And this is where you really see them become the backbone of automation. Just picture a factory assembly line for a second. You've got cylinders clamping parts in place for welding, ejecting finished products, transferring items from one conveyor to another, lifting heavy components, and pressing materials into their final shape. Their incredible versatility is really what makes modern high-speed manufacturing possible. So the big takeaway here is that these aren't just some abstract parts you only find in a factory. The next time you hear that familiar pshh sound when a city bus or a train door opens, that is a pneumatic cylinder hard at work. They are a hidden but totally essential part of our daily lives. They really are the unseen muscles of our automated world, just tirelessly pushing and pulling behind the scenes. And that's our deep dive into pneumatic cylinders. Now that you know what to look and listen for, I guarantee you're going to start noticing them everywhere. Thanks so much for joining me for this one.
Let's study more and like, share and subscribe for such more content. And comment something you want to learn.